Just a moment. Okay. So, here we are, the Calabial seminar, which is going to change to the seminar Geometry Arithmetic Differential Equations of Periods soon in the future. Anyway, today Roberto is going to talk about small codimensions of the Hodge locus. Okay, Roberto, 55, 1 hour, 55 minutes, 1 hour. Go ahead.
Okay. Thank you very much to all of you for attending to this talk. So my plan today is to talk you about my latest work about the small codimension components of the Hodge locus containing the Fermat variety. My intention is to give a kind of complete sketch of the proof of the main results. So let's start. So the first thing I want to do is to settle some questions that I believe that are the main ideas behind the proof of the result. And I believe that these questions are interesting by themselves and are very hard. In fact, they are not well posed questions. And what I want to do is to try to convince you in this talk that at least in some very special cases we can try to handle these questions, and we can use these ideas to obtain new results about some generalizations of some classical problems in algebraic geometry. So first of all, I want to recall a little bit about the Hodge cycles on hypersurfaces. So let X be an hypersurface. So it's given by the equation, by one equation, homogeneous equation in the projective space. We will assume along this talk that the hypersurface is smooth, of degree D, and of even dimension. Okay, so this is our context along all this talk. So this hypersurfaces, what it's nice about hypersurfaces is that we know how to produce nice generators of the rank homology in terms of a very simple description given by Griffith's basis. So I want to recall what Griffith's basis is. So take any homogeneous polynomial of degree d minus 2 times n over 2 plus 1. Well, the degree, you can forget about it for the moment. And we want to produce elements in the rank homology. So we want to produce differential forms. So to every polynomial, we can associate a differential form omega p that is given as the residue of a meromorphic form in the projective space with pole of order n over 2 plus 1. So this form, the degree of the polynomial is chosen such that this form is homogeneous of degree 0, right? And omega is the standard top form in Pn plus 1 of degree n plus 2. It's a n plus 1 form. So the residue will be an n form. It will be a closed-end form in the rank homology. So it will define an element in the rank homology of X. And furthermore, what Griffith's theorem says is that this form it lands in the middle part of the Hodge filtration of the rank homology of X, right? Which is exactly this. It has a middle part in the Hodge decomposition and some other extra parts. Okay. So what else we know about Griffith's basis is that its image is exactly the primitive part of the filtration, the middle filtration of the Hodge decomposition. This means that it is exactly all this filtration, except that in the middle we are taking the primitive elements. Those are the elements that are orthogonal to the polarization, which is the class coming from the the ambient space, the ambient projective space, right? So we know that this map is surjective, so every form in this filtration that is primitive can be written as a residue of this type. And furthermore, when we look at the image in the quotient, on the quotient by the next filtration, the next step of the filtration, this is isomorphic to the primitive elements of the middle part of the Hodge decomposition. The kernel of this map is the Jacobian ideal. So this is the ideal generated by the partial derivatives of f, right? And so we obtain an isomorphism between the degree sigma part of the Jacobian ring and the primitive part of the middle part of the Hodge decomposition of X. Okay. Well, so this is Griffith's basis. And well, our first question is, can we read from P, I mean, from looking at P, at the coefficients of P, at maybe some nice candidate in the Jacobian ring, right? A nice representative. Can we know if this form is a Hodge class, right? So the point is, we know that it is in the middle Hodge filtration, but it might have maybe some extra parts, not just the middle part. And the hardest part is to know if it's rational. So how can we know if it's rational or not just looking at P? So this is our first question, and well, maybe better, we would like to know if it's an algebraic class, right? Just looking at P. So these two questions, I believe they are very hard. They are not well posed at all, because there are a lot of choices that we can do here. But I want to try to convince you that in some way we can partially try to answer these questions and obtain some new results. So, well, regarding the second question, I have a result which is the following. So if we know that the form corresponds to the primitive part of an algebraic cycle Z, which is given explicitly in terms of equations, and furthermore it is a complete intersection inside the projective space, then I claim that I have a candidate for the polynomial P, which is given by a constant factor here that, well, that it doesn't matter, it's non-zero, and this is the polynomial, the structure of a representative of the polynomial, right? Where the Fi's are the equations of C, and the Gi's are the equations coming from the decomposition of F in the ideal generated by C. Okay, so this is giving us like a very, very partial answer to the second question. We know, maybe we don't know just looking at P if the class is an algebraic cycle, but we know that if the algebraic cycle is explicit enough and it's a complete intersection, we can produce one representative of the polynomial P. Okay. So now regarding to the first question, we can try to use this result to give a kind of a very, very partial answer to the first question. So the thing is that whenever we have two classes given in terms of Griffith's basis, so given in terms of polynomials P and Q, we can compute the periods of one over the other cycle, right? Or maybe the cup product. And the formula is like this. It is here we have a constant that is independent of P and Q. It's rational also. And the period at the end is given just by this relation. And this relation, as you can see, is just a relation between the coefficients of P, the coefficients of Q, and the coefficients of F. And so whenever well, since we know that the rationality of the class, that is the hard part to prove. I mean, we would like to have an omega P such that it is a Hodge cycle, and the hardest part to prove is that it is a rational class. we know that the rationality is equivalent to having all its periods over rational classes being rational, right? And so since we know how to produce some algebraic cycles, we can use them to test the rationality of a candidate of a Hodge class, right? And so whenever, the conclusion is, so whenever we know more algebraic cycles and we know how to represent their polynomials, we will obtain a lot of rationality conditions on the coefficients of P in order to obtain a Hodge cycle, right? I mean, this will give us a lot of constraints on the coefficients of P if we want to make it a Hodge cycle. Okay, so this is the philosophy. Okay, now I will move to my main results. So first of all, I want to recall the classical problem that it's about surfaces. So I have to introduce the Noether-Lefschetz locus, which is the following. It is the locus of surfaces, well, of a fixed degree D in the projective space of dimension 3, which are smooth and having a Picard number bigger than 1. This means that not all curves inside S are obtained by intersecting S with other surface. There are some other curves that you cannot obtain in this way. Some divisors which are not necessarily very ample, right? And well, what the classical Noether-Lefschetz theorem says is that whenever you take a very general surface of degree D, at least 4, then this surface will always have Picard number equal to 1. So the Noether-Lefschetz loci is the complement of this open set. Well, it's not an open; it's countable intersection of open sets. And so, well, we would like to want to understand a little bit more this space. This space is very strange. It has infinitely many components. It is also known that these components are dense in the space of all surfaces of degree D in P3. And well, it was a kind of active research topic in the beginning of the 90s. So now I want to explain a little bit which were the main, well, some of the main questions regarding the Noether-Lefschetz locus. So after the development of the infinitesimal variations of Hodge structures by Carlson, Green, Griffiths, and Harris in the 83, they were able to produce some tools in order, some tools which were useful to study this locus. So, for instance, they obtained an upper bound for the codimension of the components of the Noether-Lefschetz locus, and they ask what is the smallest possible codimension of the components of the Noether-Lefschetz locus. Okay, this is a very natural question, because if you understand what the Noether-Lefschetz theorem says, it says that well, if you take the family of whole surfaces of degree D, you know that the generic element of the family will be an element of Picard number equal to 1. But you can ask, what happens if you take a smaller family, right? If you take a smaller family, you would like to know under which conditions you can guarantee that the generic element has also Picard number equal to 1, right? And well, they ask which is the smallest possible codimension, they conjecture which it was, and it was a theorem, it was a sequence of results from due to Green and Voisin between 88 and 89, and they obtained these results are summarized in the following theorem. So the first thing is that the smallest possible codimension is D minus 3. this codimension is only attained by one component, which is this component, the component corresponding to surfaces containing a line. This is for degree at least 5, because in degree 4, well, all components has this codimension. And the next smallest codimension, this is a result due to Voisin, is 2D minus 7. And it's only attained by the following component, which is the space of surfaces containing a conic. Okay, so this is the classical results. This was one of the first questions asked about the Noether-Lefschetz locus. Well, and so the next question is what happens in higher dimension. So in higher dimension, the corresponding locus, which is the natural generalization, is the following: the Hodge locus, which corresponds to the space of hypersurfaces, smooth hypersurfaces, with non-trivial Hodge cycles. This means that the dimension of the space of Hodge classes is bigger than 1. Why? Because whenever you have a smooth hypersurface, you always have a Hodge class inside it, which is the trivial Hodge class, which is the one coming from the projective space. It's the polarization. And so, well, since we know that for dimension 2 the Hodge conjecture is true, is the Lefschetz 1-1 theorem, this Hodge locus for n equal to 2 is exactly the same thing as the Noether-Lefschetz locus. The Néron-Severi group is isomorphic to the Picard group for surface. Okay, so this is the natural space to look at in higher dimension. And after also Carlson, Green, Griffiths, Harris, the infinitesimal variation of Hodge structures, they also, the tools that they developed are also useful for us in order to study this higher dimensional space. So one big difference between the Hodge locus and the Noether-Lefschetz locus is that a priori we don't know if this Hodge locus is an algebraic variety. But what we know after Carlson, Green, Griffiths, and Harris is that it is a countable union of properly contains analytic subvarieties of the space of all smooth degree D hypersurface of even dimension n. And in fact, it is, well, these analytic subvarieties are in fact algebraic. This is a deep theorem due to Catani, Deligne, and Kaplan, but I won't talk about this because we don't need it here. So the point is that this locus is again very weird. And regarding to the generalization of the theorem of Green and Voisin about the smallest codimension component, we have this result due to Otwinowska, and later Movasati also obtained a result about this. And these two results can be stated in the following theorem. So the first thing is that in higher dimension, the smallest codimension component of the Hodge locus is n over 2, well, it's this number that is exactly d minus 3 for n equal to 2 in the following cases. So Otwinowska proved this for a very big d depending on n, and Movasati proved this for the components which contain the Fermat variety without the restriction on the degree. Okay, so these are the two cases where this result is known. Furthermore, Otwinowska was able to show that again for very big D, the only component which attains this minimum is the natural generalization, which is the space of hypersurfaces containing a linear subvariety of dimension n over 2. Okay, so now I want to explain the main ideas behind these proofs, the proof of the theorems of Green, Voisin, Otwinowska, and Movasati. So first of all, which are the main ingredients? the first ingredient is the local Hodge locus associated to Hodge site. So take now an hypersurface in the Hodge locus. I will denote it by 0, but it's any point. It's not the 0 point. It's not the 0 hypersurface, obviously. I mean, well, that's not even any hypersurface. So take any point in the Hodge locus. Since it is in the Hodge locus, we know that it has a non-trivial Hodge class, which we will denote in lambda, which it has non-zero primitive part. And to each such class, we can associate a germ of analytic subvariety of the affine space, which is defined as follows. So contain the parameters in the Hodge locus, the set of hypersurfaces, such that the lambda t, that is the natural transportation of lambda by monodromy in the deformation, is still a Hodge class. Okay, so well, this local Hodge locus now has a natural analytic structure. This structure might be non-reduced, and furthermore, the interesting fact is that this germ of analytic subvariety is well, is supported in, well, not always, but no, I want to rephrase this. Every component, every local component, every branch, every local branch of the Hodge locus at some point is given in this form, can be parameterized by some of these local Hodge locus. Okay, so to every local branch passing through a point in the Hodge locus, we can associate a Hodge class such that the local Hodge locus associated to it corresponds to this branch, or is support at least in this branch. So this is our first tool to study the Hodge locus. And our second tool is to study the Artinian Gorenstein algebra associated to the Hodge class. So if we assume that the corresponding hypersurface has an equation given by f equal to 0, and we write this Hodge class, the primitive part of the Hodge class, in terms of Griffith's basis, we know that it's given by some polynomial p lambda here that it exists. We can associate this Artinian Gorenstein ideal, J f lambda, which is defined as the quotient ideal of the Jacobian ideal of f, divided by the polynomial representing lambda in Griffith's basis. Okay, so this is an ideal inside the ring of polynomials, and it is Artinian Gorenstein, meaning that the quotient ring is Artinian Gorenstein algebra. So this is, if you don't know what an Artinian Gorenstein algebra is, what you should know is that it is kind of the algebraic generalization, natural generalization of a ring of cohomology of a compact manifold, right? It has a Poincare duality. The top cohomology has dimension 1, and after some point all the cohomology is 0. So this is a very, very nice structure. The Artinian Gorenstein algebra is a very, very nice ring. And what's the point? The point is that we can relate these two structures, the local Hodge locus and the Artinian Gorenstein algebra. We have the following relation. So first of all, we have a correspondence. Whenever we take two Hodge classes, or two n over 2 n over 2 classes, the Hodge locus, the local Hodge locus are equal if and only if the Artinian Gorenstein ideals are equal. And this is also equivalent to the fact that the classes in primitive cohomology are equal up to some non-zero constant factor. The second property, which is in fact the motivation for us in order to get to this Artinian Gorenstein ideal is that the degree d piece of the Artinian Gorenstein ideal corresponds to the Zariski tangent space of the local Hodge locus associated to lambda. Okay, so you can think about this ideal in such a way that the degree d piece is containing the information of the first order approximation of the local Hodge locus. But since we have this correspondence, in some way we should think that this Artinian Gorenstein ideal is containing more than just the first order approximation, because it is determining the whole germ of analytic variety here, right? So maybe in some hidden way it contains also the information of all other higher order approximations. Okay, but these are the main relations between these objects. And so, what is the structure of the proof? The proof of the theorems of Green, Voisin, Movassati, and Otwinowska. So we want to find a lower bound for the codimension of the components, right? Since I mentioned before, all the components, at least locally, correspond to local Hodge locus associated to some Hodge class, right? And furthermore, to each of these Hodge classes, we can associate this Artinian Gorenstein ideal, and the degree d piece corresponds to the Zariski tangent space of this component. And so, in order to find the lower bound, it is enough for us to find the lower bound for this degree d piece of the ideal, right? Which corresponds to the Zariski tangent space of the component, at least locally in a branch. So the idea is to do this, but we can do this not for any Hodge class. We can do it in general for any n/2 class, and this is what they do, right? As you can see, when we define this ideal is defined in terms of the polynomial. The polynomial, a priori, we don't know anything about it, which will tell us that it is a rational class, right? So we can pick any polynomial and define this for any class of type n/2, or in the middle part of the filtration of X. And so, well, we define this in the natural way, and we have to show this codimension. This was done by Green and Voisin for dimension 2, and by Otwinowska for bigger degree, very big degree. And what they did was to use very strong tools from commutative algebra to study in general the Hilbert function of an Artinian Gorenstein algebra in a very general setting. And as you see, Otwinowska, she was forced to obtain this result, this like more or less asymptotic result, because of the difficulty to prove this for any d. I mean, in my opinion, this problem, try to prove this for any d and any hypersurface, is a very challenging problem in commutative algebra regarding these Hilbert functions of Artinian Gorenstein rings. And probably it's not true. I mean, if you try to prove it in the generality of any Artinian Gorenstein algebra, it will certainly be false. But even if you try to prove it in this generality, I don't know if it's true. I mean, if you take any n/2 class, which is not a priori Hodge, I am not attempt to claim that this is even true in these cases. For me, it's very important, the rationality condition. Okay, this result was also obtained by Movassati's, and Movassati's approach was, well, forget about any f, take f equal to the Fermat equation, and so he also, his approach was different. He took a basis of the rank homology of Fermat, and he considered the period matrix. So the point is that the rank of the period matrix corresponds exactly to the codimension of this ideal in degree d. And so what he proved, in fact, he didn't needed to know exactly the periods matrix. He just used the structure of the periods matrix. He knew that some of the entries were 0 and some of the entries were non-zero, and using that he was able to prove this bound. So the second step is to characterize the equality. So when you try to characterize the equality, you can show in a more or less natural way that the ideals satisfying this equality are necessarily of the following form. They have a part which is generated by linear equations, and the rest is the usual Jacobian ideal. So the only thing is that you produce these linear equations and they are linearly independent. So a priori, these linear equations are not determining a Hodge cycle, right? So as you see, we started from a cycle which is not necessarily Hodge, and if it satisfies the equality, we cannot claim that it's Hodge up to this point, right? We can choose any linear equations which are linearly independent, produce this ideal, and this ideal will represent some class here, okay? And we'll also have this exactly this codimension. So up to now we haven't used at all the Hodge condition. And the third step is to define the cycle given by these equations and prove that it is contained in the hypersurface, right? After we prove this, everything is easier. I mean, we can show that the Artinian Gorenstein ideal associated correspond to the Artinian Gorenstein ideal associated to this linear cycle, and then we conclude that the Hodge locus correspondent are equal, and we obtain the result, right? So the hard part is to prove that this linear space is contained in the corresponding hypersurface. So this was done again by Green and Voisin and by Otwinowska. And how did they do it? So they considered the following map. For every element of the local Hodge locus associated to lambda, you associate this linear space, right? This Pn over 2, which a priori is not contained in the hypersurface. So it's just a map to the Grassmannian. They realized, well, this is after you consider this map, it is an elementary problem of algebraic geometry to realize that this map is surjective. Further, this gives us an upper bound for the codimension of the fibers, because we know the codimension of this locus. We also know the dimension of the Grassmannian, and so we have an upper bound for the codimension of the fibers of this map. Furthermore, you can show that the genetic fiber, well, in fact, all fibers are contained in this other algebraic variety, which is defined by a bunch of determinantal equations. So the observation of Voisin, which is the main idea behind this proof, is that if we suppose that the genetic fiber of this map is not containing in the corresponding hypersurface, I mean, not the genetic fiber, the genetic Pn over 2 is not contained in the corresponding hypersurface, then the equations defining this algebraic variety, we can show that a lot of these equations are independent, and so this will give us a lower bound for the codimension of the fiber, which will be too big, right? From here we get the contradiction, and so the point is that this what they never use the rationality of the class. They never use that the class lambda is a Hodge class. what they use is the continuity of the Hilbert function of this ideal, right? They use that it exists, this map. Okay, so this is the first observation. The continuity of the Hilbert function implies the rationality condition on lambda. Okay, so this is the idea of the proof. Now I want to state my results. So my first...
Otwinowska uses T very big here or somewhere else?
I cannot listen. Sorry.
No, Otwinowska uses this T very big in this part or in other part?
The what?
I'm talking about Otwinowska's condition, T very big. She uses
everywhere. I mean, the hard part of Otwinowska argument is this one, right? To prove that the inequality. This is the hard part, to study the Hilbert function of this Artinian Gorenstein ideal. After you have this, the second part follows more or less naturally, and after you have the second part, also the third part is more or less simple. The hardest part is this one. This is the very challenging problem, in my opinion. Okay?
Okay, go ahead.
So, so my results are the following. Well, what I did was to reconsider Movasati's approach, and I tried to push it forward, and I obtained the following results. So the smallest codimension components of the Hodge locus containing the Fermat variety is the following, is what it should be, the space of hypersurface containing a linear subvariety of dimension n over 2. I did it for any degree except by 3 cases, degree 3, 4, and 6. Okay, I will explain later why I couldn't attain these cases. And now my second result is the following. I was able to compute the next smallest codimension component, which is this number, which is equal to 2d minus 7 for n equal to 2. And furthermore, if you take any local Hodge locus which attain this codimension, I proved that there exists a complete intersection of type 1, 1, 1, 1, 2 of dimension n over 2, such that its ideal is contained in the Artinian Gorenstein ideal of the corresponding Hodge cycle. And if you assume further the following condition, that f is inside the square of the Artinian Gorenstein ideal, I am able to prove that in fact this complete intersection is contained inside Fermat, right? And so I can prove that the local Hodge locus is exactly the locus of hypersurface containing this complete intersection of type 1, 1, 1, 2. Okay. So in particular, well, what this second theorem says is that the next codimension of components passing through Fermat is attained by the hypersurface containing a complete intersection of type 1, 1, 1, 2, but it might be also attained by other component, but this component cannot satisfy this relation. In particular, it cannot correspond to a complete intersection cycle, because all complete intersection cycles satisfy this relation. So, well, I pose here the following question, which is this condition equivalent to the fact that lambda is supported in a complete intersection cycle? Well, I don't know. So I want to give the sketch of the proof of these two results. Well, in fact, I will give you the sketch of the proof of theorem 1. Theorem 2 is similar, but more technical. Okay, so let's recall the proof of the classical results due to Green and Voisin, and also the results of Otwinowska and Movasati. So this is the structure. The structure of my result is the same. So I want to explain the differences here. So regarding the first step, which is the hardest one in terms of commutative algebra tools, when you restrict to the Fermat variety, I took here the Fermat variety, well, you can study this Hilbert function of these quotient rings without too much effort, because the Jacobian ideal of Fermat is too simple. It's just a monomial ideal, and so we can use any monomial ordering and use Grobner basis and study the Hilbert functions of these quotients ideals. And so this is what I did. In order to get the second step, again, you can more or less naturally obtain that those attaining the quadratic correspond are given by these linear equations. Furthermore, the advantage of working at Fermat and using a monomial ideal is that we can obtain them as elements of a Grobner basis of this ideal, and we can use the division algorithm to write them in a very nice way, right? We can put them in this format, where this AI again is a complex number, and this number is really any complex number, right? Up to this point, we again cannot say anything about the rationality of the class. So we can just say that this number exists, but a priori they can have any value, any possible value. So the hardest part now up to this moment is to show this, that the linear cycle is in fact contained in X0. So the point is, Voisin's argument is not useful anymore, because we just know this result at the Fermat point. We don't know how to obtain this kind of bound even in a neighborhood of Fermat. This is a very hard problem. For me, this is as hard as to show the general result, I mean, at any point. So what can we do in order to avoid this argument? So again, the idea is to exploit the rationality of the class lambda, right? Lambda is Hodge. So we know that we can, these numbers cannot be so arbitrary. The other thing is that we know a lot of algebraic cycles in Fermat. As I explained at the beginning, using my theorem, we can take all the linear equations contained inside Fermat, which are explicit. We can produce their polynomials in their corresponding polynomials in the Griffiths basis, and we can compute the periods of lambda over all these algebraic cycles. And since they are rational, these numbers have to be rational. On the other hand, we can write explicitly the polynomial defining lambda in Griffiths basis in terms of the equations of the LIs. Right? So it will give us a polynomial in terms of these coefficients AI. So whenever we compute the periods, this will give us some rationality conditions on these numbers AIs. Okay, so what are these conditions? These conditions are of this form. So AI to the d-1, where x and y are these roots of -1, any these roots of -1. So we have a lot of rationality conditions, which are enough to prove that each of these numbers are in fact at these roots of -1, which is what we want. I mean, this implies that the linear cycle is in fact contained in Fermat. But we can do this just for d different from 3, 4, and 6, which traduces in the following arithmetic condition that this primitive root of unity plus its conjugate is not a rational number. Okay, so that's the idea of the proof of theorem 1. This is what I wanted to say. Well, the idea of the proof of theorem 2 is just going further and studying the codimension of this ideal in the next case, and we can do this also using this Grobner basis. It's not that hard, but we cannot again I mean the problem regarding to compute the periods in this other Hodge cycle is much harder in the next case. Okay. So well, the final comments. What happens for d equal to 3, 4, and 6? For d equal to 3, 4, and 6, there is a family. I can produce an n over 2 plus 1 parameter family over the rational numbers of n over 2 classes, satisfying all the periods condition, all these rationality conditions that appear here. I can produce a lot of classes lambda which satisfy this condition, but they are not this root of -1, right? In fact, they are an infinite family parameterized by n over 2 plus 1 parameters over the rational numbers. And in fact, this doesn't mean that the result is not true in these cases, right? What I believe is that probably these cycles are not rational classes. They are not rational because the only thing that I can check with using linear cycles is the rationality on the Hodge classes. But in order to check that a class is rational, you have to compute the periods over all the rational classes, not just those having lying in the middle part of the Hodge decomposition. And as you can see, even for degree 3 and 4, where the linear cycles generate all the Hodge classes, this is not enough, right? And so this takes us again back to our first question, which is again, how do we know conditions that guarantee that a class is Hodge in terms of Griffith's basis, right? So can we find?
Question.
Yeah.
This means that you have a variety in these I variables.
Sorry.
This means that you have a variety in these I variables, AI.
In those.
Because with this condition, you get AI to the b equal to 1, the root of unity. Yes. So this 3, 4, 6, you will get a kind of variety for AIs.
Yeah, but it's not over the complex, right? It's over Q.
Wow.
You see, it is a set having a natural action of S1. I mean the group of complex numbers having modulus 1, right? Which lie inside the ring Q Q with some root of unity, right? And this group act over this set, and well, it's not one copy of this group, it's n over 2 plus 1 copies of this group. I mean, it's the product, the power of S1 of the Q of theta d points of S1 up power to n over 2 plus 1. It's not an algebraic variety, it's not a variety, but well, it has an algebraic structure there.
Okay.
And well, this is the first comment about why I wasn't able to go further in these 3 cases. So for me, all these classes shouldn't be Hodge classes, right? The point is that we don't know how to check that they are not Hodge classes. Probably if I am able to produce some special class here that is not representing a Hodge class but is representing a other rational class, I will be able to compute the period and obtain a contradiction there in these cases. But it will be very surprising for me if these classes were Hodge, because they in that case they should be representing a very weird Hodge cycle, and I don't believe that that's the case. So the second comment is about Otwinowska Voisin argument to conclude the rationality condition just looking at the Hilbert function of this Artinian Gorenstein ideal. So the continuity of this Hilbert function, at least in low degrees, implies the rationality of lambda. This is what Voisin's arguments prove. So in view of variation of Hodge conjecture, if we believe in variation of Hodge conjecture, this is some question that should be reasonable to consider. So again, consider now a family of algebraic cycles, a flat family of algebraic cycles, and you look at the Hilbert function of this Artinian Gorenstein ideal. So is it continuous, at least for low degrees? I don't know. And the point is that for me, proving the continuity of this Hilbert function is strongly related to the Hodge condition of the corresponding cycle that you take here, right? So even if you're able to prove that this is continuous for any Hodge cycle, for me this is very close to proving variation of Hodge conjecture. And of course there are a lot of cycles which are not Hodge where this function is not continuous, right? And as I explained before, I can produce a lot of them. You just need to take these linear equations taken randomly, and you will produce some class in the middle part of the Hodge decomposition, which is not Hodge, and the Hilbert function there will be necessarily discontinuous, because otherwise Voisin argument will imply that it is Hodge, which a priori is not. So for me, the continuity of this Hilbert function is strongly related to the Hodge condition on the cycle. And well, this question should be easier to answer, and I don't know how to. I don't have any idea how to do this. And well, this was what I wanted to talk to you about. Thank you for listening.
Okay. Thank you very
And
much.
these are the references.
Okay.
Roberto?
Any question?
Sorry.
Roberto, I'm sorry. The computation of the coproduct of those forms, which came from the Griffith theorem at the beginning of your talk, it is work from Griffith and Harris, isn't it?
What? The computation of this what?
That proposition, is this part of Griffiths and Harris' paper, isn't it?
Carson Griffiths, you mean?
This proposition, from where was it taken?
No, this is not too hard to prove. I mean, this is something that it will appear in this book that we're writing with Hossein.
Yeah.
And this is also in the article that I wrote about this work. And in the article of Carson and Griffiths, you have a particular case of this, right? What they prove in Carson Griffiths is that this is zero if and only if P times Q belongs to the Jacobian ideal, right? So that result is a particular case of this, but this is not doing much more than what they do, right? It's essentially the same count, and you can find it in my article. I think that I wrote this.
Which one? I'm sorry. In this one, the one done in 2019.
Yeah, the latest one. Yeah.
Okay. Thank you.
Okay. More questions, preguntas, even very elementary. Doesn't matter. Okay, so I think I have already asked no question. No. Okay, so let's thank Roberto once again. And next week there will be talking about the first part of his project. Thank you, Roberto.
Wow.
Okay, recording.